Hello, everyone. Today I will present our work on CVPR2023 named CLIP is also an efficient segmenter, a text-driven approach for weakly supervised semantic segmentation. Our work aims to explore the potential of contrastive language image pre-training models to localize different categories, and our main contributions include: 1. We propose a simple yet effective framework for weakly supervised semantic segmentation based on frozen CLIP. 2. We propose softmax grad CAM to suppress the confusion caused by non-target classes and backgrounds. 3. We re-explore text inputs under weakly supervised semantic segmentation setting and customize two text-driven strategies, sharpness-based prompt selection and synonym fusion. 4. We present a class-aware attention-based affinity module to refine the initial CAMs in real time, and introduce confidence-guided loss to mitigate the noise in pseudo-masks. 5. Our framework achieves SOTA performance and greatly reduces the training cost. Here are our background and motivation. Semantic segmentation aims to predict pixel-level labels but requires labor-intensive pixel-level annotations. Weakly supervised semantic segmentation is proposed to reduce the annotation cost. It only requires weak supervision, such as point, bounding box, scribbles, or image-level labels. This work focuses on the last type. Previous works typically follow a three-stage framework. First, a classification model is trained on the specific dataset to generate initial class activation maps. Then, a pixel affinity network is trained to refine the initial CAMs. At last, the refined CAMs serve as the pseudo-masks to train a semantic segmentation model. Obviously, this multi-stage framework is complex and time-consuming as it needs to train multiple models for different purposes. Besides, it only works for limited categories that training data included. Recently, the contrastive language image pre-training has shown great success in zero-shot classification. It is pre-trained on 400 million image text pairs from the internet to predict if an image and a text snippet are matched. This dataset-agnostic model could transfer to downstream datasets directly and realize open vocabulary recognition. In this paper, we aim to explore the localization ability of CLIP for arbitrary given classes and use it to tackle weakly supervised semantic segmentation tasks through well-designed texts. To this end, we designed several strategies to adapt CLIP to weakly supervised semantic segmentation to improve accuracy and efficiency. Now we will introduce each of them. GradCam is widely used to identify the discriminative regions for the target class by the weighted combination of feature maps. It uses the gradient information to compute the class feature weights in equation 1, and the CAM can be obtained as equation 2. CAM generated by original grad CAM is only determined by the target class. It lacks competition among different classes and tends to result in category confusion, as shown in the figure. We introduce softmax function into grad CAM to make different classes mutually exclusive. And the weight of feature map becomes into equation 4. It indicates that the weight of the target feature map will be suppressed by non-target classes. So the corresponding CAMs of the target class can be revised by the remaining classes. We also define a background category set to eliminate the interference of common class-related categories. Our framework could enjoy multiple merits inherited from CLIP by designing specific text inputs. For prompt, we find that prompt ensembling can outperform every single prompt by a large margin for the classification task on ImageNet, but takes no effect on multi-label dataset in weakly supervised semantic segmentation. We suspect this difference is primarily due to the varying amount of labels per image. The dataset used in weakly supervised semantic segmentation is multi-labeled, and all target classes in an image should be concerned. We designed a metric, namely sharpness, to measure the distribution of target class scores for multi-label images using different prompts. Assuming there are n images in the dataset and k classes in an image, the sharpness based on a specific prompt can be calculated as equation 5. In the right figure, we compare sharpness and corresponding segmentation results among 20 prompts. The result demonstrates that our proposed metric is roughly negatively correlated to segmentation performance. Consequently, sharpness can serve as convenient guidance for prompt choice, and only image-level labels are needed. For class names, since the category names provided in the datasets are limited, we use synonyms to enrich semantics and disambiguate. Besides, we find the performance of some classes can be further improved by customizing specific words. For example, by replacing person with clothes, the masks can cover the whole body. The initial CAM is coarse and should be refined by similarity between pixels. Previous works train a separate affinity network to achieve it, which is time-consuming. In contrast, the attention mechanism in Vision Transformer can reflect similarity between patches. However, the original multi-head self-attention is image-level and class-agnostic, while the CAM is class-wise. Leveraging MHSA directly may amplify noise by propagating noisy pixels to its semantically similar regions during refinement, as is shown in the figure. We propose class-aware attention-based affinity to improve vanilla MHSA. It finds regions of target class in the format of box based on CAM and use it to mask MHSA. In this way, a pixel in CAM will not be affected by class-irrelevant pixels, and falsely detected pixels in CAM can be suppressed for their weak affinity to the target object. Note that we extract the attention map and CAM with the same forward pass. Hence, CAA refinement is real-time and requires no additional stage like previous works. Each pixel in the CAM indicates the confidence of this position belonging to the target class. Most methods generate pseudo-masks from CAMs by simply setting a threshold to distinguish target objects and backgrounds. It may bring noise into pseudo-masks because those positions with low confidence are too uncertain to belong to the correct class. We propose a confidence-guided loss to ignore those unconfident positions when computing loss. We can find that unconfident pixels mainly focus on object boundaries, which is reasonable because boundaries tend to be semantically murky regions. Here are our results. We first evaluate the quality of generated pseudo-masks. In Table 1, our method outperforms previous works by a large margin. When using these masks to train a segmentation model, it also performs well. Besides, our work is based on CLIP and requires no extra training during mask generation, so it is efficient in terms of time and GPU memory. This page presents some ablation studies. All of them have a positive effect on the final result. That's the whole presentation. For more details, please refer to our original paper.